Hello, everyone. Welcome to another awesome video for contemporary math. This is in section 4B for the book that I use. Otherwise, we will call it the power of compounding. And this strong arm here with the dollar sign on it, that is absolutely on point. So let's begin with few definitions. So we have these definitions here. In financial formulas, the principal is the starting amount that is borrowed or invested. If you have a mortgage, you know what a principal is. If you have a car loan, you know what a principal is. If you are investing money, you know what a principal is. So it's the amount that you're starting with. Then from there, we have two different types of interest. We have simple interest, is interest paid on the original principal only, and compound interest is interest either paid or earned on the principal and any previously earned interest. So I want to make sure I say this as well. These words can be interchanged, or paid and earned can be used in either scenario for either compound or simple interest. So if you lend somebody money, of course you will earn some interest back. And if you borrow money from somebody or some entity, you will pay interest to them. So it could go either way. So to put this into context, we are going to look at example 1 here and just sort of get across the idea of what the difference between simple and compound interest is. All right, so Jason borrowed some money from Uncle Vito for 3 years at a simple interest rate of 10%. And I want to point out that this is an annual rate. There we go. It's an annual rate. So that means every year, Jason will be paying this amount of it, 10% of interest. All right. So let's say for year 1, we will take the principal and we will multiply it by the rate as a decimal, and we will get $200. So the first year, Jason borrows money from Uncle Vito. After year 1, Uncle Vito comes, knocks on his door. Hey, you know you owe me $2,200 now. All right, so Jason is working to get this money back. Sure. But this brings up a really nice formula for you. This is the interest known as I. And in a simple interest formula, the interest can be found by multiplying the principal times the rate. All right. So, year 2, Jason still only borrowed the original $2,000. So for year 2, it's going to look very similar. Because Jason only owes Uncle Vito the $2,000, he keeps paying the 10% of that $2,000. So another $200. So again, this is another interest equals P times R. Well, if it's going to be the same for every single year, year 3 will look exactly the same. So, I mean, why bother doing all of this every single time when Jason will just be owing the same amount of interest each year? So interest for a year is P times R. Cool. How can we figure this out so that we would know we could do this faster? I think we can say that the total interest is P times R times the number of years, right? If we add all this up, it's 200 plus 200 plus 200, that's 600. Couldn't we have just multiplied the $200 from 1 year by 3, because there were 3 years, and just gotten 600? Yeah, So the yearly interest, so that's a total interest over there. This is the interest for 1 year would just be P times R. The total interest would be P times R times T. And again, to answer the question, how much interest will he be paying for borrowing the money? $600. Cool. If he intends to pay his uncle back in full 3 years from now, what will he owe his uncle at that time? Here we go. Hey, yo, Jason, it's Uncle Vito. You owe me, well, it would be the original amount that he borrowed plus another $600. You owe me 2,600 bucks. So there it is. So if we wanted to know the total amount that Jason would owe, I'm going to use the letter A for accumulated amount. It would be the principal, right, how much Jason borrowed, plus PRT, right, principal plus the interest, the total interest. All right, so that's simple interest. It's not too bad. Compound interest gets a little more interesting, and I think Uncle Vito will like compound interest more. So if Jason had to pay 10% interest compounded annually, how much interest would he pay for borrowing the money? All right, so year 1 is going to be exactly identical. So there we go. We found the P times the R. But here's where it gets different. This interest gets added into the principal. So year 2 is not $2,000. The principal is not $2,000 anymore. For year 2, the principal will be $2,200. So compound interest adds in the interest as the calculations go, whereas simple interest kept the principal the same all 3 years. So when you multiply $2,200 times 0.10, well now, instead of the $200 we had in year 2 back here for simple interest, now Jason owes $220 for that second year. And what happens? Same thing. This gets added to the $2,200, and now after year 3, Jason would now owe an additional $242. So the interest from year 1 was now being charged interest, and the interest from year 1 and 2 was now being charged more interest. Uncle Vito's going to make way more money here. So here's what's happening. To answer the question, how much would Jason pay Uncle Vito, or how much interest would he pay? This would be $662. That is $62 more than simple interest. The interest helped Uncle Vito earn more interest. So what would the total amount be? Well, the accumulated amount would be the principal plus the interest made, which in this case would be the $2,000 that was borrowed plus $662, which would be $2,662. And if I were Uncle Vito, I would use compound interest for sure. For the next example, you see we have example 2 here. This says, while banks almost always pay compound interest, bonds, which is an investment tool used by big companies and people can invest in bonds, usually pay simple interest. So suppose you invest $1,000 in a savings bond that pays a simple interest of 2%, that pays simple interest of 2% per year. How much total interest would you receive in 5 years? If the bond paid compound interest, would you receive more or less interest? Explain. All right, so let's use that formula that we had above for the simple interest. The total interest, remember, equals P times R times T. So since you are investing $1,000, that would be your P, you would multiply that by the 2% interest rate times the number of years. So the rate is 0.02, the number of years is 5. And when you multiply all these things together, you get, what was that? 100. $100 in interest. How much money did you start with? Remember, your accumulated amount will be P plus the total interest. So the accumulated amount is 1,000 plus 100, which is 1,100. $1,100. Okay. Let's check to see what you would get if you were going to get the interest as compound instead of simple. So for the first year, you would get $20. Okay, you would add that to the 1,000 and get 1,020. And you would multiply that by 0.02. So here you would end up with $1,020. We'll keep a running total. All right. So you would have $1,020 times 0.02. That would give you $20.40. So if you add that to the $1,020 you already have, that would be $1,040.40. So then you take this new amount, 1040.40, you would multiply by 0.02, and you would do this until you hit 5 years. It would look like something that looks like this. So all I've been doing is multiplying the current principal at the end of the year times another 2%, finding the interest and adding it to this amount here, the previous year's ending amount. So add these two, I got this. Find the new amount of interest using this number, add these two, I got this. Find the new interest amount using this number, add these two, get this, so on and so on and so on. So you can see that this amount is a little bit bigger than this amount. In fact, it's only about $4.08 more. Over a 5-year period, that's less than an extra dollar per year. I mean, it's something, but it's not. It doesn't wow me. So, did you get more? Yeah, but more money is always better. I don't know. You guys can make your own mind as to which one you would like in real life. So yes, you would get, to answer the question up here, compound interest would earn you more money over simple interest. Also, consequentially, compound interest would also charge you more money than simple interest if it was a loan. All right, so on this slide, this one's going to go by much faster than the first one, I promise. On this slide, we have the compound interest formula for interest compounded once per year. So here it is. So if you thought it was a great big hassle to be figuring out how much interest was made each year and then add it to the new principal and then use the new principal to find out how much interest we made that year and add it to the new, I mean, it's a long process just to make out this table where you figure out the interest, you add it together, and you get P plus I, blah, 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 blah. It was just too much, that last example, the compound interest. Luckily, we have this formula here. This will do it all for us in one step. So A, as I've been mentioning, is the accumulated balance after 10 years. P is the principal. APR is the annual percentage rate as the decimal. And Y is the number of years. Pretty straightforward. I was using T in the previous examples. Y is what we will be using from here on out. So example 1, example 2, using the compound interest formula for interest compounded once a year. Here we go. I can just substitute in some numbers. I got A, the ending amount, is 2,000. So that's what is here. And then I'm going to just write a set of parentheses, 1 plus 0.1, the interest rate, close parentheses, raised to the third power. So I can simplify what's inside there. This would be 2,000, 1.1 to the third power. And that gives me, you guessed it, 2662.00. Just like what we got on the previous slide. And then we can do the same thing for the second one. I can write that the A, the accumulated amount, is the original investment or the principal times 1 plus 0.02 to the fifth year, right, to the fifth power. I can combine everything in this set of parentheses, 1,000 times 1.02 to the fifth power. And guess what? The accumulated amount is about 1104.08, just like we found out in example 2. Pretty cool. So there's a formula for that. You don't have to do all the table like what I was explaining. Like what I was explaining up here. So it turns out that we have a very similar but slightly different formula. We can have the compound interest formula for interest paid n times per year. So normally the most common one would be monthly. And when we say n times per year, n could be, we can say semi-annually, n could be quarterly, monthly, weekly. I mean, there are lots of different ways to break up a year. Daily, so on, so on, so on. I'm going to tell you, in the real world, the most common one is monthly. If you have a savings account, if you have a credit card, if you have a mortgage, you only get charged your interest one time per month. So with all of these different descriptors come different values. So here, semi-annually, how often or how many times would something that happens semi-annually happen in a year? Well, it would only happen twice a year. How many times, if something happened quarterly in a year, how many times would it happen? 4 times in a year. If something happened monthly, how many times in a year would it happen? 12 times. Weekly? Funny story, I had a student that didn't know that there were 52 weeks in a year. I think the student said 46 or something like this. I was like, what? And daily would be 365 times per year. In the formula, you can see the only difference is that we divide the APR by this n, and we multiply the y, the number of years, times the n. And that is because if you, let's think a worst case scenario. Your credit card charges you 24% interest on your purchases. I'm going to go ahead and bet that you would not want to be paying that 24% every single month. because that's what would happen if this n weren't here. Then you would be paying 24% every month. What this n guarantees is that, let's see, 24% would be 0.24. Credit cards charge monthly, so this is annual. So if we divided this by 12, which is what n would be if we picked monthly, we would get that we would get a new rate, 0.02, but that would be your monthly rate. And that would make you feel a lot better. So instead of being charged 24% every month, they would take the annual percentage, which is how your credit card would give you this interest rate. They would take this percentage and divide it by 12. That way they aren't charging you all 24% every single month. Nobody would be able to afford a credit card. But at 2%, no problem. You can make payments on that. So we make that division here. It benefits you if you have a credit card, that division happens. So why does n happen up here? Well, back in the equation up we were looking at up at the top, it was just y. And that's only because you were getting interest once per year. But think your bank account this time. If you get interest 12 times per year and you only have it for 1 year, 12 times 1, you would still be guaranteed to get all 12 interest payments. So this n multiplied by n helps you, if you have a bank account, to get you more interest. So here we have an example, example 3. It says, Grandma and Grandpa want to put some money away for college for their brand new grandchild. They deposited $20,000 in a bank account that pays an APR of 3%. Compounded monthly. Ooh, I'm going to do this. There we go. Over 18 years. So that's another piece of good information. We have another piece of information here and here. All right. How much will be in the account when their grandchild turns 18? So what I'm going to do, just to make sure I get all my information down, I am going to write, let's see, APR, everything from the other side of this would be N, this would be Y. And I'm going to fill in everything I know. So I know that the P was 20,000. I know the APR was 3%, which more specifically we want as a decimal. So 0.03. N is 12 and Y is 18 years. And N is 12 because we said monthly. If something happens monthly, how many times in a year would that happen? 12. All right. So we can start by, well, we already started. We can continue by writing out our equation. A equals P times 1 plus APR, PR over N to the NY power. Next, I'm going to fill in all the numbers that I know. This would be 20,000 times 1 plus 0.03 divided by 12 to the 12 times 18 power. I'm going to simplify a few things, so I will have 20,000. 1.0025 and 12 times 18 is 216. So now that I have this in some sort of workable form, I can put this into the calculator and get approximately $34,297.02. So I am out of space, but if you went through and did this annually, I encourage you to try that yourself. You would only get, let's see, this would be annually, you would only get $34,048.66. So what this example is wanting to prove to you is that the more times you compound in the same number of years with the same interest rate and the same principal, the more times you compound, the more money you'll make. And that's a good thing. That's good for you to know. If somebody offers you a savings account and they say, we'll compound it annually, and you go to another bank and they say, we'll compound it daily, and everything else is the same. The interest rate is the same. You're going to bank with that bank the same amount of time. You're going to invest the same amount of money. You're going to want to pick the bank that will give you the daily compounding. But you can keep increasing the compounding and the number of compoundings and the number of compoundings until you're basically always earning interest. As time passes, you're earning interest. And that's what compound interest formula for continuous compounding is. So we have this weird thing here. Here it is. We have E coming back. E is about 2.71. But again, on a calculator, you'll want to find that button that looks something like this. It will have, it might be above a button on your calculator. It might be printed above a button. So you're just going to have to find out where it is. But that E takes care of all the compoundings, and you notice there's no N listed here because N is gone. If you're always earning money, you don't need an N. It's already calculated into the formula. So let's take a look at this last one. I mean, the formula is super similar. We have A equals P times something to a power, the APR times Y. So all we have to do is write all these things down for Sandy and Jack and Jill, and we can get to moving. So again, I'm going to write down all of my little variables on the side. I'm not going to write the E because the E doesn't change. It's always going to be 2.71828. So let's read. Sandy is planning on buying a car in 5 years. She deposits $6,000 into an account with an APR 4% and continuous compounding. Those are the words right there. These words tell you you will be using the E equation I just took off screen up there. How much will she have to purchase, how much will she have to purchase a car in 5 years? All right. So the beginning amount was $6,000. The APR is 0.04, aka 4%, and we're looking at 5 years. So this formula looks like this. This would be 6,000 E raised to the 0.04 times 5. And all of this is in the exponent. So what you will do then is you will do 6,000 E 0.20. You want to multiply these things together and then just plink it into a calculator to figure out what that is, because I don't know how to raise E to any power except for 1, because E to the first power is just 2.71. But if you plink it into a calculator, she will have $7,328.42 saved for a car. So how much interest did she earn? Well, she ended with this amount, 7,328.42. She started with 6,000, so that means she earned $1,328.42 in 5 years. Hey, that's pretty good. That's like $250 a year, a little more, maybe $260 a year. That's pretty good. For nothing, she just let her money sit in the bank. All right, last one. Jack and Jill got married. They planned to buy their first condo in 4 years. So that looks like some important information. I'm going to give that an underline. 4 years. They have researched accounts and they have narrowed it down to 2 options. The first account offers an interest rate of 5% compounded annually. All right, so here's one scenario, 5% compounded annually. The second account offers an interest rate 4.75% compounded continuously. So that's a completely separate scenario. If they want to accumulate a down payment of $20,000, accumulated $20,000, how much must be invested for each option? Which is the better deal? So let's do this one, annual. I have A, I have P, I have APR, and Y. So this time we know the accumulated amount. We don't know what the beginning amount is, right? It's even asked that. How much must be invested? We don't know that. The APR for the annual rate is 0.05, and there are 4 years to earn money. So this is going to look a little bit different. This will be 20,000 equals P times 1 plus 0.05 raised to the 4th power. Again, we don't need N here or here because it's only happening once per year. It is an annual rate. So I guess we just have to go through and figure this part out, which would be 1.05 to the 4th power times P equals 20,000. And now, most of the time, all the previous examples, we would just multiply everything on the right side out. But we can't do that this time. Instead, what I want to do then is figure out what is 1.05 to the 4th power equal to? And it is 1.21550625. And you want to go out as far as you can with these decimal places because you want to have an accurate answer. So now this is a pretty simple equation to solve though, because we have the variable times something. If we just divide by that number, we can figure out what P is. So we're going to divide by that number so it will reduce to 1. And on the the left side of the equation, we will see that P equals, it would be $16,454.05. So I want you to pause the video. I want you to try the continuously compounded version of this, which would use the same formula we did here, except A would be replaced with 20,000, and then you'll just figure out the E to some power and do some dividing. Go ahead and give it a shot.